Welcome to Python Basics with EJD. Still talking about Python packages. This is one of my favorite packages, SciPy for computing. And that for scientific computing, that's what we'll be discussing in this video, SciPy for scientific computing. Of course, as you know, I'm just doing a kind of overview of some of the most important Python packages that you can use. I mean, I've been through some that I've never used before, just to intimate everybody with that. But SciPy, I've used SciPy a couple of times. In fact, I just finished the playlist on spectral analysis, and SciPy is pretty useful in that regard. So what does SciPy do? Of course, in summary, scientific computing, but at the nitty-gritty, talking about the nitty-gritty of what it does, SciPy builds on NumPy to provide a powerful ecosystem for numerical computations, data analysis, and applied mathematics. It contains specialized submodules that simplify complex tasks across integration, differentiation, optimization, probability, statistics, and signal or image processing. Now, I have a playlist on scientific computing with Python. So I started a journey. They're trying to look at the very key submodules of SciPy. The playlist it started a long time ago, and I've not completed it. So I hope I complete it one day soon. All right, so let's look at one of its capabilities. Of course, I mean, what I'll be doing here is nothing near the total capabilities of SciPy, but I'm just going to brush over this since this is under Python basics. So just to introduce you, in case you're a mathematics enthusiast or like an engineer, an applied mathematician, or something like that, or you use maths in some form, or you do scientific computing, physics, engineering, and all that. Okay. So we can use SciPy for integration, differentiation, and numerical methods. So talking about integration, we can have single integration, like you can do SciPy integrate dot quad, which handles definite integrals of one variable. But of course, it's always going to return to you numerical values. In the next video, I think we'll be talking about SymPy. SymPy deals with symbolic Python. So it will give you results in form of symbols, like, if you differentiate x squared, you get 2x, that kind of thing. But here you are doing numerical integration, differentiation, and all of that. So talking about multiple integration, you can use things like DBL quad, TPL quad, and N quad, which allow double, triple, and n-dimensional integration. So you can do ODE solving. So you can use solve underscore IVP, which solves ordinary differential equations for systems of equations. So taking an example, imagine that you want to, of course, from SciPy, of course, if you don't have it already, the first thing to do is to do pip install SciPy. Well, I have it installed already. That's why I don't want to bother. So pip install SciPy. All right. So from SciPy.integrate, you import quad. Okay. Then you import NumPy as NP. I have a feeling I should demonstrate how to install for some weird reason. I wonder. Let me just go ahead and do that. So if you don't have, if you are using SciPy for the first time, so you need to do pip install SciPy, pip install SciPy. So for any package at all, you do pip install that package. So of course I already have it. So it's going to most likely tell me something like, oh, requirements satisfied or something like that. But if you are doing it for the first time, it will take a bit more time. And the report is also going to be more, right? So pip install SciPy is the requirement is already satisfied. So now I'm talking about from SciPy. So having installed now, so each time you need to use it, you now need to import it. Or if you need some specific tools from it, you need to get that specific tool, like what we have here now. So we say that from SciPy.integrate. So because we are focusing on integration, right? So because we are doing integration in this situation, so from SciPy.integrate, you now import quad. So, and you have import numpy as NP. So you have f lambda. So this is a special function that we are declaring. And if so lambda x. So we define x as exponents of e raised by minus x squared. So the function we are defining is e raised by minus x squared. And the way to get it, we need exponents, and we get it from numpy. That's why we need numpy here. And then this lambda tells us we are doing a special function. So if you don't understand what this is about, you can check I think, the 24th video in this series where we talked about Python functions. So you can use Lambda functions to define some special functions that you need to quickly deal with. Okay. So what we want to do now is to want to integrate e raised power minus x squared, over the whole interval, over some interval from 0 to infinity, basically from 0 to infinity. I think that's the Gaussian equation or so, if I'm not mistaken. I think that's the Gaussian equation. So here in line 6, that's where the real work is happening. So in line 6 now, we get result and the error attached to it, and then we use the quad that we've imported from SciPy.integrate. So we take the function, which is e raised power minus x squared, now defined in line 4. So, and we integrate it over 0 to infinity. You can only get infinity from numpy. That's why we say npy.inf like that. So we just run this and it's just integrate it numerically, and we get this value 0.88622. And that's why here it's approximately 0.8862 for integration. Then coming for differentiation now. So that's talking about numerical differentiation, by the way. Like I said, SciPy does numerical stuff, numerical differentiation, numerical integration, numerical methods. So for differentiation, you can have numerical derivatives using scipy.misc.derivative. That's for basic finite differences. So you can also have automatic differentiation. While SciPy does not provide symbolic differentiation like SymPy, it provides approximations useful for optimization and root finding, right? So imagine this example, we need to, so from SciPy.optimize, import approx._f prime, right? So we now import numpy as np, and then we have f. So we quickly define this lambda. We need sine x squared. Normally, if we differentiate sine x squared, that should be 2x cos x squared, right? So, but then we want to integrate that numerically. So we say print approx_f prime. So f prime is like differentiation. Of course, this is a bit different from SciPy derivative I talked about. Well, I think that wasn't working, so that's why I had to go for this. Then you differentiate this function, right? And then you have a tolerance limit of 1 e raised power minus 6, right? Okay, up here we only printed the results. So we could actually, we had results and error. So we could print the results and the error attached to it together. I think that's important because when you do numerical stuff, you want to see. So you see the error now. So you see the error attached. So the result is this, and the error is 7.10, blah blah blah. So when you are doing numerical procedures like this, you are interested in the error, and that's what we have right here now. Okay. So having done that, then we come for the differentiation thing. So here we want to approximate derivative at x equals 1. So it's more like, so this sine x squared, and I said if you differentiate it, it's like function of a function. So you differentiate the x squared, you get 2x, and you differentiate sine x, sine, you get cos. So that's like 2x cos x squared. So you now want to do that at x equals 1. That's like at x equals 1, we should get 2x cos x squared. So x squared, put 1 as that's 2x cos 2 times 1 cos 1. That's 2 cos 1. So whatever cos 1 is multiplied by 2, that's what we're going to get here. And then we have the tolerance limit here. So it tells us, so we get 1.080607 like that. Okay, I think can we try to evaluate? Let me create a new cell and just see, since we know the answer directly, can we just have 2 times x times cos, can I just say cos 1? I think it's going to work in radians or something. Okay, I've not defined the x. 2 times 1 cos 1, yes. 2 times 1 cos 1. 2 times 1 cos 1. Okay, I need to get cos from numpy, right? So, so you see the result now. So it's 1.80. So this is the direct thing, because when you differentiate sine x squared, you get 2x cos x squared. So you can see how the result is what it is in that situation, 1.080. But of course, we have some differences like that here because of the tolerance. So if I increase the tolerance, maybe it gets closer to this. Maybe if I make the tolerance like let's say minus 15, it will get closer. Oh, it's almost like 1.1. Okay, so no stress. Let's leave it the way it was. So then SciPy can do optimization And talking about optimization, interestingly, I have a playlist on optimization, and I have on numerical optimization techniques, linear programming, and then I have numerical optimization techniques, right? So for optimization, we have things like root finding. So I have a playlist also numerical analysis where I talks about things like Newton-Raphson, seconds, and Brent method. Okay, I didn't talk about Brent method, but I talks about bisection, seconds, Newton-Raphson. So what we need in that case is the scipy.optimize.root_scalar or scipy.optimize.fsolve for finding the zeros of a function. Then you have unconstrained optimization. So you can minimize with algorithms such as Nelda, BFGS, and conjugate gradient. Then you have constrained optimization. So like linear and nonlinear constraints supported. So you have SLSQP. I think I dealt with this in under the numerical optimization techniques, kind of. Then you have the trust constraint. Then applications, you have it in curve fitting engineering design, and economic equilibrium. Then you have least squares and curve fitting. So you have curve underscore fit, nonlinear least squares. Then you have least squares for robust regression. So, and a good example here would be to optimize, imagine this function and use lambda function to define x minus 3 squared plus 1. Okay, so of course, this is a simple function that can easily be differentiated and evaluated at x equals 0. So imagine to differentiate this now, we can do function of a function. We have bring down the power. So that's 2, differentiate x, that's 1. So you have 2 into x minus 3, then the 1 is gone. So for 2 into x minus 3, so at x equals 2 into x minus 3, right? So for 2, when x of 0 is 0, right? So you have 0 minus 3, that's minus 3. All right. So minus 3, okay. Yeah, it's like so differentiate equates to 0, get x, I think. So you have 2 into x minus 3 equals 0. So that'll be x equals 3 in short. So x will be equal to 3. So if you now substitute the 3 back, so 3 minus 3 is 0. 0 squared is 0 plus 1. So when you differentiate this and evaluate at 0, you get 1. That's what we should expect to get. All right. So this is where the actual minimization is now happening here. So you have res equals minimize f x naught equals 0. So we are evaluating at 0. So we expect the answer to be 1. So the minimum value. So you can see when you differentiate this and equate to 0, you're going to get x equals 3. That's why you have this 3 right here. And then the value of the function itself at that point is this 1. That's what happens in optimization. Then SciPy is good for probability distributions and hypothesis testing, right? So for probability distributions, you have over 100 continuous, like SciPy, star, norm, exponent, gamma, etc., and discrete distributions. So you have binomial, Poisson. So functions include, so for other functions, you have PDF, probability density function, CDF, cumulative distribution function, and RVS, random sampling. So for hypothesis testing, which SciPy also does, you can have parametric tests like t-tests, individuality test and all that. ANOVA, you can have non-parametric tests, like Man, Whitney, you, Kruskal, Wallis, Wilcoxon, signed rank. I did all this under my statistics playlist containing like 25 or 35 videos, I'm not sure now. And you have the goodness of fit, where you have chi-square tests and all that. So let's do a simple example. So we have scipy.stat. So these are statistical in nature, by the way. So you have scipy.stat, and then you import test underscore int, then you have the norm. So import numpy as np. Then from here, now you have x is norm. So norm talks about normal distribution, as you can imagine. So then you generate two samples. You have x, you have normal random variables. You have LOC 5 scale 2 size 100, then another one LOC 5.5 scale 2 size 100. We can visualize this too if you want, by the way. So we have two sample t-tests, right? Okay, let me cut this out. First of all, let's just try to visualize these two. So I just say x comma y, and I run this, and then you see we have the two. I mean, it's 100, right? Or maybe we can see them one after the other. Let's see x first. So this is what x looks like, and this is what y looks like. Okay, but then so those numbers have been generated like that. Then we want to do two sample t-tests. We want to test between the two. We want to find the p-value. We'll calculate a test statistic. So the actual place where that is happening, we have the statistics, we have the p, and then we do the t-tests, of comparing the y and X and Y, right? Normally, t-test should happen for like 30 anything less than 30 samples. But of course, I'm sure if you do t-test for values greater than 30, you're also almost going to get like what you should get in a Z-test. So it will help us calculate the statistics and the p-value. So we run this, and this is what we get. So you have statistics, you have minus 2.04, blah, blah, and p-value 0.04, whereby by standard, the p-value has to be less than or equal to 0.05 for it to be significant. And this one is it 0.0 or 0.005 or something like that? So then we now use this to determine whether there's a significant difference between the two samples. Then you can use SciPy for signal and image processing basics. I mean, we use this a lot under the spectral analysis playlist. So for signal processing, like Fourier transform, so you have things like scipy.fft, parc.fft, IFFT. Then for filtering, you have SciPy. You filter signals of unnecessary frequencies. So you have scipy.signal.butter. You have L filter, fields for digital filters. And you have spectral analysis, which that playlist was about. So you have power spectral density with Welsh. So SciPy does all of this. So you have a very good example here. So we have of course, from SciPy.signal, import butter, filter, and Welsh, import numpy as npm, matplotlib.pyplot as plt. Then you generate a noisy signal. So you have the frequency sample 1000, sampling frequency. You have the time, which is from 0 to 1, and then you have the signal, which is this X now. So it's a signal with two frequencies and some random noise, right? So it has frequencies 50 and 120. I think we dealt with that a lot under spectral analysis. Then you have the low pass filter cutoff equals 0.2 of Nyquist frequency. So you have BA. So you do all of this, and then you now plot the spectral density. So, and that is shown by this periodogram, right? You have the frequency and the periodogram using that Welsh method, and then we plot the results like this. So if you run this now, okay, so you will see the signal filtering. So the noisy signal is the blue signal, but the filtered signal is the orange one, all right? The filtered signal is the orange one. After we have filtered it out like that, so you have the noisy and the filtered signal, okay? So we have all of that, as you can see here. So Y is the filtered signal, as you can see, because we have applied fields to it. And then secondly, we have the power spectral density using the Welsh approach for spectral density, which would have taken care of some variance troubles like that. And then, we have all of this going like that. So for image processing too, interestingly, we can use SciPy for image processing. In the video I did on scientific computation, I think under interpolation, we saw how we can actually use we can use SciPy to interpolate, and then do some transposition or so on an image. So that was quite an interesting point in that series, right? So for image processing, we have basic operations like blurring. You can use SciPy for blurring, sharpening, and edge detection in images. So you have functions like scipy.ndi_image.gaussian_filter for blurring. You have scipy.ndimage.sobel for edge detection. You have scipy.ndimage.rotate for rotation. You have scipy.ndimage.zoom for rescaling. And you have applications in medical imaging, computer vision, processing. A very good example, of course, in this case now, you've seen a lot about this image thing. So we need to install scikit image. So that's the first thing you should do if you don't already have that. So, and here it tells me requirement already satisfied because I had it installed before. So that takes us to, so we just go straight and do some image thing. So we want to blur an image, we want to rotate it and everything. We're going to get that image so first of all, you say from SciPy import NDI image. So NDI image tells us, okay, with NDI image, you can do all of these four things, right? So, and then you now import skimage.data. So from skimage.data, you can have a sample image for whatever you need to do, right? Of course, matplotlib.pyplot is good for plotting, for showing the image if possible. And then you load the sample image now. So image is skimage.data.camera. Then you apply filters and transformations like blurred. So to blur it, you have ND image.Gaussian underscore filter image. Sigma is 3. Edge is NDI image.Sobel image. Rotated. So this same image you've loaded here. So edges now, you have NDI image, rotated NDI image or rotate image. So you can rotate at 45 degrees, you can rotate at 90. You can keep changing this to keep rotating and all that. Then you're not reshaping because reshape is false. You can also zoom it. So NDI image or zoom, you can have image zoomed at 0.5. You can change these values to see what happens. Then you can plot the result. So you have figure in our distance. So we want to do a 2 by 2 plot. That's 2 rows and 2 columns because we have the original. Oh, okay. I guess we don't have the original image. We have the blurred image, the edges, they rotated and zoomed like that. So we use all of this. So we have blurred edges, rotated and zoomed. And we now iterate over this whole thing now. So for AX in axis.ravel, axis.axis of, then you plot and the type layout and show the images. So that takes some time. And then we have the images. So you can see the images like this. So here now we have the blurred image right here. We have the edges here. Then we have the rotated image. We have the zoomed image. So let's see what we can tweak from what we saw the other time. For sigma, for the blurred image, can we set sigma to like 7? Let's see what that work does. And let's rotate the picture by 90 degrees, right? That would be remarkable. So now you can see the image has been rotated by 90 degrees. And then you can see the blurred one, it's not as clear as it was, when we had sigma to be 7. What if I make sigma 1? Is it going to be a bit clearer? Yeah, it's clearer now. So the sigma value, the higher the sigma, the worse the image would be for the blurring. So I can actually rotate this at angle 1, maybe even 270 degrees. 270 degrees. Okay. So that will flip it around like this. So we can work on images with SciPy. So in summary, we see that we can use SciPy for integration and differentiation, integration and differentiation help approximate mathematical models when closed forms are unavailable. Then we have we also have that optimization, which enables solving engineering, physics, and economics problems. We have statistics and hypothesis testing, which support data analysis, inference, and research. We have signal and image processing, which connects SciPy to real-world applications like biomedical, seismic signals, and computer vision. With this, I come to the end of this interesting video on SciPy for scientific computing. So SciPy is a Python package for scientific computing that can handle integration and differentiation, optimization, statistics and hypothesis testing, signal and image processing. All right. Thank you so much for listening to this. Let me know how helpful this is for you. And if there's something else you haven't tried, feel free to let me know. If you want to learn more about SciPy, you can check my playlist on scientific computing, which was done a long time ago. So just check on playlist and you see right there. Okay, if you have subscribed already, thank you so much. If you haven't subscribed, of course, you'll be missing a lot. So just go ahead and subscribe and don't forget to hit the notification bell so that you can always get alerted each time a new video is released. And having done that, things can even get better if you click the join button and become a member of this channel. And it comes with some special privileges for you. So just check out all the perks awaiting you. Okay. Ultimately, don't forget to like, share, and comment so that more people can have access to the great content I have going on here. Till I come your way again, keep doing Python, right? Don't forget, in the next video, we'll be talking about SciPy, which works with symbolic mathematics. Bye.